So this video is my BCR 4.1 alternative mastery video. So this objective is going to be covering understanding nuclear reactions and radioactivity by explaining what subatomic particle is affected during a nuclear reaction, being able to compare the energy being released from a nuclear reaction to a chemical reaction, understanding what it means for nucleus to be unstable and how that relates to the balance of attractive nuclear forces and repulsive electrical forces, understanding what it means if an element is radioactive, and understanding the process of radioactive decay and how it affects the atom and how that relates to radiation. So radiation is anything that radiates out of the nucleus. So over here, this is our radiation, and it's the energy being released from this unstable nucleus we have here. So you might see in many nuclear power plants, they're just sites sites where they use nuclear equipment, like in hospitals, X-ray rooms, stuff like that. It can this danger sign, and that is because it can do damage to your body. So it could possibly kill you because it is so dangerous. It has a very small range, so once it's released, it can't go very far. Radioactive atoms the atoms that release the radiation. It has a very wide range, so it can go really far. And when it's released into the environment, it can coat things, which will go into your body. So it's kind of inevitable. It'll coat your food, it'll go inside you. And once it's inside you, it'll release radiation in a very harmful manner. And it will mess with your DNA and break it, and not break it, but mess with it. So in conclusion, radioactive atoms are the atoms which release radiation. Since radiation cannot travel very far, it is the radioactive atoms which can cause most damage to our body and our health. So when they coat your food, when the radioactive atoms coat your food, it's very easy for them to go in your body because it's in your food, which will go in your body, and then that way it can damage you, cause cancer, and other diseases, and kill you. So, what subatomic particle is affected during a nuclear reaction? Well, if you mess with the number of electrons, you get a different ion. If you mess with the number of neutrons, you get a different isotope. But if you mess with the number of protons, you get a different element entirely. And that is what we deal with when we're dealing with nuclear reactions. We're changing the number of protons. So in this example of a chemical equation, during nuclear reaction, we start off with uranium. And after undergoing the reaction, we end up with two completely different elements, thorium and helium. So we mess with the number of protons. And when we mess with the number of protons, we change the identity of the atom and the element. So this is why we changed the number of protons. We ended with different elements. So they're in a chemical reaction versus a nuclear reaction, which one has the most energy? Well, in a chemical reaction, this is best shown. The energy required is best shown through an equation. So over here, both sides are balanced. So we start off with sodium, phosphorus, oxygen, magnesium, and chlorine. And we also end with sodium, chlorine, magnesium, phosphorus, and oxygen. So there's same elements on both sides. The type of the atom didn't change, but the form of the atoms did change. So we have different compounds. And the mass is conserved. So over here, we have 6 sodium atoms, and over here we also have 6 sodium atoms. This the law of conservation of mass applies for all chemical equations. A good example of this is baking soda and vinegar. So During this reaction, we start off with two compounds. And after undergoing the process, we have like different compounds, but they're still the same elements. Nuclear action, on the other hand, is very different. There are different elements on both sides. So in the reactant side, we have uranium, and on the product side, we have thorium and helium. The type of atom has changed because we have a completely different element, and the form of the atom is also changed. However, in this, the mass is actually conserved because in uranium, the mass of this isotope is 238 because it's uranium 238. On the result side, we have on the product side we have thorium has a mass number of 234 plus the helium mass number, which is 4, which equals 238. The number of protons in uranium is 92. And on the product side, the number of protons in thorium plus the number of protons in helium is also equal to 92. An example of this is nuclear weapons. So the reason nuclear weapons is in the news so much and is so catastrophic is it because it requires like so much energy is released in the reaction. Because we're changing the element altogether. We're changing the protons. We're changing the identity of the whole element. So it requires lots of energy for this to happen. In conclusion of the statement, a nuclear reaction has more energy released than a chemical reaction. So when you have an unstable, a nucleus is unstable when you're changing the number of neutrons. And like I said earlier, when you mess with a number of neutrons, you end up with a different isotope of the same element. So you could have hydrogen 2, you could have hydrogen 3, it's kind of endless. So a nice example of this is a simulation I have here. So we received a simulation in our ASPT unit, which kind of taught us about isotopes. And this is a great demonstration of unstable isotopes. So here we're messing with the number of neutrons, and we have now it's unstable, like right here. So once you mess with the number of neutrons, you get an unstable isotope. So this relates. An unstable nucleus is relating to radioactivity because when a nucleus is unstable, these protons, they have the same charge. They both have a positive charge. And as we all know, when two charges are positive, they repel. So these positive charges want to repel, but the nucleus needs to be contained. So we need a force stronger than this electromagnetic repulsive force, and that is the strong force. The strong force, since these these protons are trying to repel each other, we need something 100 times stronger than the electromagnetic repulsion, which is a strong force. By saying the strong force has a short range, we mean that once the strong force is gone, it's no longer applied. So it's not like this is still being applied, even though the protons are repelling each other. It's completely gone. So what is exactly a radioactive atom? Well, in this example of uranium, there's so many protons which need to be cannot be contained permanently. So when the binding force or the strong force is not strong enough to contain the nucleus permanently, the element or atom is radioactive. So when we say an element's radioactive, we're saying that it can't it's so unstable that it cannot possibly be contained by the strong force or any other kind of binding force permanently. So all elements above atomic number 83